Okay, now we want to find the maximum possible, the temperature at which we get the maximum possible practical efficiency, I call it. It's not the thermodynamic efficiency. That's just a little bit different. In this case, it won't be a whole lot different, but there's a difference. So by the practical efficiency, we mean the change we accomplish in mechanical energy divided by the amount of heat we put in, the energy we get out per unit of energy we put in. So you should think about how you're going to do that. We have the expression for the potential energy change per unit of heat added. How do we maximize it? Well, just a simple exercise in calculus. We take the derivative of the quantity, and right here it is. I've written it out a little more clearly than before, just because I had a little better board space to do that with. Okay, but here it is. How do we take the derivative of this? Well, it's very, very simple. It's derivative of the numerator times the denominator plus the minus the derivative of the denominator times the numerator, quotient rule, something you're very confident with. So let's just write it out. The derivative of the numerator is this. The derivative of the denominator is this. I'm not going to read it to you. That's a simple derivative. Everybody would get that immediately. So what's the derivative of the whole thing? Well, just keep our wits about us and write it out. Here's the derivative of the numerator. Here's a copy of the denominator. Minus the numerator times the derivative of the denominator. I'm sorry, the derivative of the denominator times the numerator. Okay, read that wrong. Divided by the square of the denominator. And that square of the denominator isn't going to be particularly important in finding the temperature at which this system maximizes. Okay? Well, the critical point occurs when the numerator is 0. The denominator is not 0. Unless TF happens to equal T0, I think. Okay? The denominator is not equal to 0. So the numerator, setting it equal to 0, well, the numerator, we were kind of hoping it might be quadratic so that we could use a quadratic formula to solve it, and it turns out it's cubic. You can see that from the fact that right here you have a t multiplied by t squared, and over here you have a t multiplied by t squared, but that divides out. Okay, I mean that's 2t squared, and that's a minus 2t squared. So it looks like the only t squared term, t cubed term we have is here. So I was wrong about this being cubic. So let's fix this. No. It's quadratic. Okay. Now in class, we went a little further. I actually, on the thought that it was cubic, which I assumed without thinking or without actually checking it out. I went to a computer algebra system because cubic is solvable, but it's way worse than the quadratic, and nobody ever remembers how to solve a cubic. So that is the point at which it would be appropriate to go to a computer algebra system. However, it turns out that it's not necessary. So I'll probably do an extension video where we do that and a couple of other things to kind of help wrap this whole heat and thermodynamics and fluids section up.